Good day, stats enthusiasts. Welcome to this AI-assisted learning session. Today, we'll explore a powerful statistical tool, the Shapiro-Wilk test, under normality testing. Picture this, you're in a class. Suddenly, your teacher announces a surprise 100-item math test. You had just one night to study. Panic, maybe. Cramming, definitely. Now imagine we collected those test scores. What we want to know is this. Do these cram scores follow a normal distribution? Let's call this session Exploring Normality in Math Test Results After Cramming. Today, we are using a hypothetical dataset from students who crammed for a surprise math exam to explore how to check data normality using JAMOVI. So, what's in it for you today? By the end of this session, you will be able to understand the concept and importance of normality in statistical analysis, interpret and report the results of normality testing accurately. But before diving into powerful tools like t-tests or ANOVA, there's one crucial question you need to ask. Is my data normal? So what does normal really mean in statistics? Well, we're talking about the normal distribution, also called the bell-shaped curve or the Gaussian distribution, a symmetrical continuous distribution determined by the data's mean and standard deviation. Now, what does normal really look like? It means the distribution is symmetrical, forms a neat bell curve, and has one clear peak. The mean and median sit right in the center. It stretches out toward the x-axis but never touches it. When standardized, it has a mean of 0 and a standard deviation of 1. But wait! Before testing anything, your data needs to meet certain requirements. First, your observations must be random and independent. Next, you should be working with continuous data. And finally, your sample size ideally falls between 30 to 300 observations for best results. Now, there are two ways to check for normality: graphical methods and statistical tests. Let's start with visuals, like giving your data a quick checkup. A histogram should show a smooth, bell-shaped curve. A QQ plot should have points aligning closely with the diagonal line. A box plot should show a centered median and balanced whiskers. These methods help spot skewness or outliers at a glance, but they don't provide statistical proof. That's where statistical tests like Shapiro-Wilk and Kolmogorov-Smirnov come in. These tests calculate whether your data significantly deviates from normality or not. The two most commonly used ones are the Shapiro-Wilk test and the Kolmogorov-Smirnov test, or KS test for short. Let's begin with Shapiro-Wilk, a favorite among researchers, especially for smaller datasets. Shapiro-Wilk is best for small to medium samples, ideally less than 50 observations, and assumes continuous and independent data. KS test works better with larger datasets, typically 50 or more, and is more suitable when data don't contain many identical values. Like Shapiro-Wilk, it also assumes continuous data. Finally, their interpretation follows the same basic rule. If the p-value is greater than 0.05, we fail to reject the null hypothesis, meaning the data do not significantly deviate from normality. If the p-value is less than or equal to 0.05, we reject the null hypothesis, suggesting the data are not normally distributed. Alright, enough theory. Let's bring this to life with a real application. In a classroom experiment, 50 senior high school students faced a surprise 100-item math exam after just one night to study. The test covered algebra, geometry, and statistics, simulating the real stress of cramming. Students ranged from consistent top performers to confident last-minute reviewers. But instead of asking if cramming worked, we'll focus on something statistical. Do their scores follow a normal distribution? When testing for normality, of course, we start with hypotheses. Whenever we run a test like Shapiro-Wilk, we're testing this. For the null hypothesis, the data is normally distributed. And for the alternative hypothesis, the data isn't normally distributed. So the hypothesis from this context is that, for the null hypothesis, the math scores after a crammed review are normally distributed. And for the alternative hypothesis, the math scores after a crammed review are not normally distributed. Using JAMOVI, we'll run descriptive statistics and perform the Shapiro-Wilk normality test to analyze the data visually and numerically. Let's begin by opening the JAMOVI application. Once you've launched it, insert your dataset by clicking the three lines on the upper left of the tab, and select Open and then browse to find your dataset. Once the data is in, click on the Analyzes tab at the top, then go to Exploration and select Descriptives. In the left panel, drag your math exam scores variable into the Variables box. Then, under the Statistics options, make sure mean, median, mode, standard deviation, and Shapiro-Wilk test are selected. Also, click the option Plots to show its content and check the options under histogram, which are the histogram and the density plots, so we can visually inspect the distribution. There you have it. Let's begin by interpreting the descriptive statistics of our dataset. As shown, we have a sample of 50 students' math exam scores, with no missing values. The mean score is 60.9, the median is 61.0, and the mode is 60.0. These three measures of central tendency are closely aligned, which already suggests symmetry in the distribution. The standard deviation is 12.5, indicating moderate variability in the scores, and the scores range from a minimum of 30 to a maximum of 88. Now, let's examine normality using the Shapiro-Wilk test. The test results show that since a Shapiro-Wilk W equals 0.995, with a p-value of 0.999, we fail to reject the null hypothesis because the p-value is greater than 0.05, which means the data does not significantly deviate from a normal distribution. According to the ARPA 7th edition format, we interpret this as follows. The distribution of math scores from students who crammed to review was not significantly different from a normal distribution. The Shapiro-Wilk test statistic with 50 participants is equal to 0.995, and the p-value was 0.999. The histogram confirms this. A bell-shaped. This confirms that the data is suitable for parametric tests that assume normality. And there you have it, normality, unwrapped. Before running any major statistical test, pause and ask, does my data follow the curve? Skipping this step is like building without checking the foundation. Remember, statistics isn't about forcing data to fit. It's about listening to what your numbers are really saying. And testing for normality. That's the first step in learning to listen well. So next time you're ready to run a test, pause, check the curve, and let the data speak first. Until next time, in another exciting episode of parametric testing, dear stats enthusiast.